So before telling you about the hidden ones, let me just quickly tell you about the boring ones, or the not hidden ones. Theories of massless particles have a symmetry where you can rescale everything. Of course, they're Lorentz invariant, but you can also rescale everything because there's no masses that set any scales. There's an extension of this, which is more surprising and non-trivial. They have invariance under inversions, which is this sort of remarkable symmetry that takes a point in space-time and replaces it with x over x squared. If you didn't know about inversions, you know about it if you solve for the problem of the electric field outside the bounded conducting sphere, which when you use the method of images only works, actually because the theory has conformal invariance. As I said, everything that ever looks like a trick is actually associated with a symmetry. So if you solve the problem in this way, you discover the symmetry of inversions. Anyway, so together these things are called conformal symmetry. And it's a symmetry that Lorentz invariant theories of massless particles are expected to have. I can't talk about twistor theory in 30 seconds, but let me just tell you, since I said that twistors have become very important again, what they're important for here, just ignore the content of the slide, but what they're important for, which is one of Penrose's original motivations, is that they're the best possible variables to use to talk about conformal symmetry. The way we just talked about conformal symmetry a second ago has a big asymmetry between translations, rotations, Lorentz transformations, and inversions. They all look very different from each other, and yet they all group into this nice big symmetry. So the twistor variables are just the best possible way, the best possible variables to use in order to describe conformal symmetry in a nice way. Okay? So that's why it's so useful in this business. But that's the obvious symmetry. The amazing discovery was that there's another conformal symmetry. And in fact, there's a completely different space-time on which this physics seems to live. Not our space-time, but a totally different space-time. In order to motivate this, remember that we had these external gluons cycled around with the natural ordering 1, 2, 3, up to n, just associated with their color. So let's take the momenta of the gluons and draw them on a four-dimensional sheet of paper. So here's P1, P2, P3, P4. Momentum conservation tells us that these momenta close into a closed polygon. Okay, so we have this nice closed polygon. So we can, if you like, draw this picture by actually giving a bunch of points, x1, x2, x3, x4. These are not points in ordinary space-time. There are just some auxiliary four-dimensional piece of paper that we've written down. The units of these x's are units of momentum, not position. Okay? But using these, I can say that the momenta are xa plus 1 minus xa. That guarantees that the polygon closes. Okay, so you can do that. But the amazing theoretical experimental observation by people actually doing calculations was they found that the amplitudes had conformal invariance in this space. Not the original space-time, but in this space. Totally shocking. In fact, because of that, they wondered, okay, well, the original space-time, you call it an amplitude. You think there's gluons coming in, they bang into each other, and all this stuff going out. They discovered that if you never wrote in the first space-time, if you only drew this picture, you would ask a second very natural question. Like imagine that there's a colored particle that you're dragging along this loop, and calculate the Aronoff-Bohm phase that's associated with the quantum interactions dragging around that loop. So this is called the Wilson loop, just think of it as an Aronoff-Bohm phase. That computation gives you exactly the same answer as the scattering. So that's just an absolutely amazing thing. You think, oh, it's gluons coming in for sure. Look, they're coming in, they bang into each other here, they do this, and they go out. But someone else would be like, oh yeah, I'm dragging this particle around the Wilson loop, and I'm getting this answer. Then you compare the actual functions and they're identical. Like, oh, which one is it? Is it gluons or is it the thing going around the loop? Well, it's both. One description isn't more fundamental than the other one. Now, the way this was actually really sharply discovered is that the symmetry was observed to be true term by term in that BCFW form of the tree amplitudes. So every one of these terms would seem to be actually invariant under both the original conformal symmetry as well as this dual conformal symmetry. So now their purpose in life becomes much more clear. That's why they're not local. They don't give a crap about space-time. They don't give a crap about either space-time. They just know about all the symmetries that are actually there. But they can be put together in some beautiful way to get objects that have a local unitary interpretation. Now these two symmetries, the conformal symmetry and this dual conformal symmetry, don't commute with each other. And they actually close into an infinite dimensional symmetry. That symmetry has a name. It's called the Yangian algebra. There's many other things I can say about it, but let me just say that this symmetry is totally invisible in the Lagrangian. This is a property of tree amplitudes, gluon amplitudes. It could have been discovered by Yang and Mills, but it had to do a lot of work. But it could have been discovered in 1955, 65, 75, 80. It could have been discovered at any point in time. It was discovered in 2007, just because there started to be some clues for where to look. But it's a symmetry that's totally obscure when you write down the Lagrangian, but it's actually there and it's a property of the answer. Okay. Now, how am I doing for a time here? Okay, so I think I will not have, well, okay, so at least I set up, that was the introduction. Let me just give you a, I'll just fly through the rest of these slides, and anyone who's interested in discussing more, I'd be happy to chat a little more after the colloquium. But I just want you to get a flavor of what's lying behind all this. So that's now all the data. And now we can start talking about where it could all be coming from. Is there actually a formulation that makes all these symmetries manifest, that makes the simplicity manifest? But clearly, if it's going to do that, it can't put in either locality or unitarity as a fundamental building block. And at least part of the story, the part that I've spent most of my time thinking about over the past number of years, involves a totally new object. It involves a new mathematical structure, actually a very old mathematical structure that mathematicians, algebraic geometers started studying in the mid-1800s, known as the Grassmannian. Grassmannian is a space of k-dimensional planes in n dimensions. If this sounds weird, that something so abstruse as k-planes and n dimensions are going to have anything to do with anything, it is weird. Okay, it is definitely weird and unusual, and one of the really interesting things that is going on here. But just to give you just a flavor of why k-planes and n dimensions should have anything to do with anything, I want to back up and just spend 2 minutes thinking about momentum conservation. Okay. Something as dull seeming as momentum conservation. Why should we get any mileage out of thinking about something as dull as momentum conservation? Well, normally, it seems like it's dull, but that's what normally happens when you reformulate things. Things that are obvious in one language become unobvious in the other language, and vice versa. And in particular, momentum conservation is normally so obvious because we have the inside of the space-time to play with, and we see translational invariance. If we don't have the inside of the space-time as a key feature of the theory, momentum conservation is going to be interesting. So to start thinking about momentum conservation, I just want to think about what the external data looks like. So these are the variables. We have the functions of these lambda variables and the lambda tilde variables. These are both two-dimensional vectors. So let me take one component here, the A equals one component. If I take these n numbers together, I can just draw those n numbers as an n-dimensional vector in a plane. The other component is another n-dimensional vector in a plane. But under Lorentz transformations, those vectors will change, but Lorentz transformations act as 2x2 linear transformations. So they change what the vectors are, but they don't change the plane that's spanned by the vectors. So just the external data is associated with this two-plane in n dimensions. So that's why something like k-planes in n dimensions might have anything to do with anything. Just the external data is associated with the two-plane in n dimensions here, and another two-plane in n dimensions for the lambda tildes. And momentum conservation is just a simple geometric statement. These planes are orthogonal to each other. And our story begins by thinking about this picture of momentum conservation in a new way, by saying not that lambda and lambda tilde are orthogonal to each other, but that there's a third object, a k-plane in n dimensions, general k-plane in n dimensions, which is forced to contain lambda and be orthogonal to lambda tilde. And then off we go. So I won't have time to describe any of this, but you say it and you start saying this in equations in a simple way. You write these things down. You see that they look very beautiful and simple in twistor space. So whatever you're doing is sensible and has conformal symmetry. You realize that there's many k-planes that satisfy this property, so you should integrate over the space of k-planes in some way. You wonder, is there some natural way of doing the integration? You start talking to some of your mathematician friends who tell you that the natural way of thinking about measures in these kind of projective spaces is to specify the places where they have singularities. And you find that actually you stumble onto something that the mathematicians turn out to have described in a different way just around 5 years ago. You stumble into an object in the Grassmannian, a polytope that lives in the Grassmannian, which is the most natural generalization of what you would think of as a triangle or a tetrahedron or a simplex. These basic notions in ordinary spaces generalize in the Grassmannian into this remarkable, rich, sort of combinatorial polytope. And that's associated with the natural form on this space that you integrate over. So, after playing these, after you think about momentum conservation in a new way, this picture of k-planes in n dimensions that you integrate over, you run into this object, and then you discover to your astonishment that this object knows about scattering in the supersymmetric theory, not just at tree level or one loop, but to infinite loop order. That equation contains information to all loops. And you also, well, and there's a lot to say about it, but the other thing we realize about it quickly is that this object is manifestly dual conformal invariant. So what it really is the object that makes this infinite dimensional symmetry totally manifest. But it makes the symmetry manifest at nowhere did I say anything like space-time or path integral or quantum mechanics or unitarity. I just wrote down this integral. It has the symmetries totally manifest, but certainly space-time and locality are not manifest. And you think about it a little bit more, you realize that just playing with natural operations, you take one polytope and another polytope, there's natural ways of gluing them together to get a bigger polytope, there's natural ways of chopping off faces to get lower polytopes, and you just put these operations together purely naturally. It's a natural combinatorial set of operations. You can define how to get the object with any number of particles, any k, any number of loop order, by gluing together lower point things with a sort of classical-like piece and a quantum-like piece. This generalizes these